In this video, I am going to explain how the recurrence relation can be solved using substitution method. This is the example problem. Example 1, the recurrence relation is T of n equals to T of n minus 1 plus 1. Here the decreasing function is involved in the recurrence relation. Let's solve this using substitution method. The given recurrence relation here is T of n equals to T of n minus 1 plus 1. The condition here is when n is greater than 0. When n is equals to 0, which is a base case, we have to write the complexity is going to be 1 some constant time, which is 1. It can be any constant value. Here the 1 is given. That is the base case. When n is equal to 0 is a base case. When n is greater than 0, this function is applied, this equation is applied. Let's solve it using the substitution method. Here in the given relation T of n equals to T of n minus 1 plus 1 is given. We need to know now to solve this relation, to derive the time complexity. We need to know what exactly this T of n minus 1 is. We know what is T of n. Now we need to find what is T of n minus 1. So T of n minus 1 can be written like this. In the place of n, if you substitute n minus 1, that is going to be the T of n minus 1 equation, right? So in the place of n, you substitute T of n minus 1. So here again there is n minus 1. In the place of n, if you apply n minus 1, you would get n minus 2 plus 1. So you know what is T of n. So you can derive what is T of n minus 1 is. For example, take this as equation 1 and this is equation 2. So this is the given question. In the given question, only if you know what is T of n minus 1, the complexity can be derived. You know what is n, you need to know what is n minus 1. T of n minus 1 can be computed like this. T of, in the place of n, if you substitute n minus 1, T of n minus 1 equals to T of n minus 1 is going to be n minus 2 plus this 1 will be retained. So this is what T of n minus 1 is. Now we know what is T of n minus 1 is. Now you substitute this equation on this one. Substitute equation 2 in 1. Now you get in the place of T of n minus 1, T of n equals to, in the place of T of n minus 1, T of n minus 1 equation can be written T of n minus 2 plus 1 plus this one we are supposed to retain here. So you would get the resultant relation is going to be T of n minus 2 plus 2 you would get. This is going to be equation 3. Again you have T of n here. If you want to derive the complexity, again you need to know this recursive function, what is T of n minus 2 is. Find out what is T of n minus 2. Again in the place of n, you substitute n minus 2 in this equation. So T of n minus 2 equals to T of n minus 2 minus 1. In the place of n, we are supposed to substitute n minus 2. So n minus 2 minus 1 is going to be n minus 3 plus 1. We got the equation for T, what exactly this T of n minus 2 is. Now you substitute equation 4 in equation 3. Because we know what is T of n minus 2 is, we will substitute now. T of n equals to, instead of this T of n minus 2, substitute the entire equation of 4, because we have T of n minus 2 here. T of n minus 3 plus 1 plus retain this 2 here. So now the resultant equation is T of n minus 3 plus 3. This is equation 5. Again to solve this, because it is a recursive call, right, it keeps on going, we keep on calling the function until we reach the base case. Again we need to know what is T of n minus 3 is. T of n minus 3 equals to, again substitute this n minus 3 in this equation in the place of n. T of n minus 3 minus 1 is n minus 4 plus 1, equation 6. Now you got it, right, T of n minus 3. Substitute 6 in 5. Now T of n is going to be, in the place of T of n minus 3, substitute this equation. T of n minus 4 plus 1 is what T of n minus 3 is, and retain this 3 here. So you would get now T of n minus 4 plus 4. This is equation 7. Again you need to know what is t of n minus 4 is. So, it keeps on going like this, right. So, you need to identify the pattern, you need to end it till when it would keep on going till we reach the base case, right. So, if you see t of n minus 4, again it is 4, it is like whatever the value we get here in the decreasing function, this and the constant is going to be outside the function call is also going to be same. So, till when it would keep on going till n minus some k value it would go plus some k, right. So, it can be written like this, t of n equals to t of n minus k plus k. So, when it would end, when we reach the base case given here is when n is equal to 0, when n is equal to 0, which means when this term becomes 0 means that we have reached the base case, the algorithm would end, the derivation would end, right. So, when it would become 0, shall we write like this, n minus k equals to 0, which means we can write it as n equals to k. So, in the place of n the k can be substituted, in the place of k n also can be substituted. So, for example, okay, for instance I am taking in the place of k I am substituting n, this entire term would become 0, right, t of 0 plus k equals to, in the place of k I am substituting n. You know what is t of 0 is, already it has been given in the base case. When n is equals to 0, when n is greater than 0, we are supposed to follow this equation. When n is equals to 0, the complexity is going to be 1, some constant time. So, when we reach the base case, the value is 1 plus you retain this n. So, 1 plus n is the final complexity, ignore the constant. So, finally, you can retain this n, which is going to be the final complexity for the given recurrence relation. So, this is how you are supposed to solve the recurrence relation where the decreasing function is involved using substitution method. Let us discuss another example in the next video. Thank you.